So from this time forward, which is about 1998, we concentrated all effort into studying vertical motion of the torso as the best movement indicator of lameness in horses. We quickly realized that although we knew the most sensitive indicator of lameness in horses, or we knew what body movements were the most sensitive indicators, we didn't know what it was about vertical torso movement that meant lameness. So as an example, here are 4 examples of vertical head movement signals in horses with mild forelimb lameness in the upper left through increasing degrees of lameness to severe forelimb lameness in the bottom right. So for instance, we didn't know if it was the maximum values. Should we look at the maximum values? Should we look at the minimum values? Should we look at the difference between the two, which is sort of the range of movement? Should we look at the area underneath the curve? Or should we look at the frequency of the signals? Obviously, the frequency of this signal is different than the frequency of this signal. In other words, at this time, we knew what to measure, but we still had no definitive idea about how to analyze the signals that we captured. So we had to go back to the drawing board, but now we collaborated with mechanical engineers. Mechanical engineers are very good signal processors. We supplied them with our vertical torso movement signals and basically just said, okay, here's our signals from horses that we think are sound. Here are our signals from horses that we think are lame. What is it about these signals that mean or signify lameness? And also that means or signifies lameness on the right and lameness on the left. They determined pretty quickly, and this kind of stuff is easy for engineers, that this was a typical fault detection problem, which is a type of frequency or vibration analysis. Finding faults in structures using vibration analysis is a common and important problem in engineering. It is used routinely to find faults in structures like bridges, foundations, airplane wings, etc. And the basic concept relies on the fact that when you stimulate a structure, they vibrate. In other words, they move back and forth or up and down like a sine wave. And if that structure is flat and undeformed, then the vibration response is very simple, perhaps harmonic with a single frequency, like a perfect sine wave that has constant frequency and amplitude. If you bend or deform that structure in any way, then when it is stimulated, its response is now not normal, simple and sine wave-like. Now its response is perturbed and more complex with added components at different frequencies. And you can inspect this perturbation, and by inspection of this perturbation, you can be informed about the location and severity of the deformity in the structure. So, the signals from the inertial sensors that are placed on the horse's torso are analyzed using this type of fault detection. And the torso moves up and down in a trotting horse twice per stride. It's like a slow frequency vertical vibration. This vertical movement is simple and harmonic with one primary component in a normal horse, a sound horse. With lameness, that normal, simple harmonic motion is perturbed, and the vertical torso movement signal becomes more complex with added components that perturb the normal expected vertical movement. Later, we determined that using this fault detection approach, not only could we measure the amplitude or severity of the perturbation, in other words, the lameness, but that by analyzing the shape of the components of the signals, or more specifically by measuring the phase differences or the timing differences between the components, that we could determine when the fault, in other words, the lameness, was occurring during the stride cycle. Was it occurring, was it perturbing the normal vertical movement signal during the first part of stance? In other words, was it an impact lameness, or was it occurring during the second part of stance? In other words, was it a push-off or lack of impulsion lameness?